In this lecture, we continue our examination of correlation and regression analysis applied specifically to the current pandemic, the current COVID-19 pandemic. And so one other approach that can be used is to answer a different question, and that question deals with the effectiveness of COVID-19 related vaccinations. And so a very common question that is posed is whether the COVID-19 vaccine works. And to answer this question, it depends on the type of research study. The first study that we'll address here very briefly is what's called the RCT, the Randomized Control Trial. And this type of research design is one that establishes cause and effect and is the type that is necessary for pharmaceutical companies to obtain government approval for new drugs. And so companies must carry out these types of research designs in order to achieve that and obtain that government approval for use of various medications, including the COVID-19 vaccine. So the RCT is considered the gold standard in research designs, whether it's a COVID-19 vaccine, another type of drug, a psychological or a psychiatric type of treatment, or any intervention in the present day should be examined through the RCT. And the RCT generally involves study volunteers, and these study volunteers are randomly assigned to two, sometimes more groups. But one group will receive the actual medicinal ingredient in this example here with an injection. Another group assigned to the placebo group would also receive an injection of a solution, but that solution would not have the medicinal ingredient contained within it. The volunteers would then be followed up for months, and the outcome variable is infection and illness. And so by following these research participants, those that report a positive COVID test or a positive infection and subsequent illness can be tracked back to the number of individuals that were assigned to the drug group or the placebo group. And as such, the establishment of whether a new drug or a new vaccine is efficacious or its efficacy is established. And that question basically deals with whether vaccines or other drugs are effective. And so the results of these studies, some are very conclusive, others indicate that the effectiveness is not ideal, and other studies would show a small level of efficacy. But we then move on to the use of correlational studies. So can correlational studies assist with our understanding of how drugs can affect the incidence of human disease? And so correlational studies can be used to examine historical data with the important understanding that this type of approach would not establish cause and effect. And so taking a correlational approach would examine previous outcomes of data that were already available. And in doing so, this is the forecasting type of approach in which the past predicting the future, and so the overarching question of whether this is a possibility. And so we take a look at some data here that were once again available at the Johns Hopkins Resource Center. And in these data here we have a scatter plot of new infections over a 28-day period for that period ending September 15th, 2021. And the vaccination rate as a percent of the total population is used as a predictor variable for the new infections over that 28-day period. And of course what you see here is a scatter plot, and we have a line of best fit. And so this line is described by this equation, and as you can see, it's a linear equation with an r squared, or an effect size, of 0.0459. And the blue diamonds here represent the data for 158 countries. And so each country reported a vaccination rate as of September 15th, 2021 as a percent of the total population, and each country had reported a number of new infections over the previous 28 days per 100,000 individuals. And so in this example, a Microsoft Excel was used to fit the line of best fit and generate these regression statistics. And so with the r squared as the effect size, if we take this value and multiply it by 100%, we would have a value of 4.59%. What that tells us is that the variability in new infections over that 1 month period among the 158 countries, 4.59% of that variability is accounted for by the differences, or the variation, in the vaccination rate of those 158 countries. And so we then would take this and compute the R value. So we're going in a reverse direction here. Typically we carry out the correlation analysis first before moving on to the regression analysis, but because a computer program was used to compute this directly, we can then use the R squared value to go backwards to the correlation. So to calculate the correlation coefficient, the Pearson product moment correlation, we would just simply take the square root of 0.0459, and that gives us a correlation of 0.214. And so this would suggest to us that this is a weak to moderate correlation, probably more on the weak side. And so the direction here of this correlation, because we take the square root of this value, we don't know if this is a positive or negative value. And so we determine the directionality of it because the slope in the equation of 4.8675 is a positive value. So we know that this is a direct correlation. And so the units of the slope are new infections per vaccination rate. And so what this positive slope would suggest is that those countries that report a higher vaccination rate as a percent of the total population predicts a greater case count over the previous 28-day period. And so the next question we ask is if this relationship, as reported, is statistically significant. And that leads us into what we call hypothesis testing. This is statistical hypothesis testing, not research hypothesis testing. And so we set up the question here, if whether there is a statistically significant relationship between country vaccination rate, that was our predictor variable, and the 28-day new case count, which is our criterion variable. Our sample size is 158 countries, and our correlation coefficient is 0.214. So it's a low correlation coefficient, but we want to determine if it is statistically significant. And the first step is to set up what we call the null hypothesis, and is always stated the same way. In this case, our null hypothesis is stating that the relationship between these two variables in the total population of all countries, and of course we did not sample all countries, but in this case it's the correlation coefficient for the population using Greek letter rho is going to be equal to 0. That tells us that there is no relationship between the two variables. We then state the alternative hypothesis, in which we state it is not equal to 0. And so because we don't know of the direction of the relationship, then we would just take a non-directional approach. And so by taking a non-directional approach, instead of stating rho is less than 0 or greater than 0, we just say it's not equal to 0. And this is an advantage because it opens up the possibility on our statistical testing that the relationship could be positive or it could be negative. And to determine if the relationship is statistically significant, we would need a table of what are called critical values for R, remembering that R was the correlation coefficient. The first step is to calculate what we call the degrees of freedom. And for correlations, the degrees of freedom is n minus 2. And we subtract 2 from the sample size of 158 countries because we have two variables. We have an x and a y. And each variable will have its own degrees of freedom. And in this case, we have 158 subtract 2. That gives us 156 for the degrees of freedom. So now we go to a very standard table, which is our critical values. And if we go along the left-hand side, we see for each degree of freedom, there are a range of different critical values. And if we scroll down the table, we see this table is limited at a degrees of freedom of 100, knowing that the one we calculated in our study is far above 100. But we can use that limit here to continue testing our study if the results are statistically significant. And we select alpha 2. Alpha is the symbol for what we call the type 1 error rate. And 2 indicates that it's non-directional, so that the results could indicate that it's a positive correlation or a negative correlation. We keep our mind open to that possibility. And we typically choose, in most research studies, choose an alpha level of 0.05. And as we go down the table here, so here we see degrees of freedom of 1, 2, 3, 4, 5. These degrees of freedom would indicate that our study has a very small sample size. But because we have a fairly large sample size in 158 countries, that we determine the degrees of freedom to be 156, we move down the table and we see the general pattern that the critical value to achieve statistical significance gets smaller and smaller and smaller. And because the table is limited at 100, we see a critical value of 0.195. So this is the value we want to zero in on. And now what do we do with this value? Well, recall that the observed R value, not the R squared, but the observed R value was 0.214, so a weak correlation. The critical value with 95% confidence, we say 95% confidence because that's the difference between 100 and 5%. For a degrees of freedom of 100, because that's where our table is limited, is 0.195. And what we determine here is that the observed value is greater than or equal to the critical value. So as long as the observed value is greater than the relevant critical value, then that would indicate that the result is statistically significant. So what we see here is that as long as that observed value is greater than or equal to the critical value, that indicates that the result is statistically significant. So leading us to conclude that there is a statistically significant positive relationship between a country's vaccination rate and the 28-day new SARS-CoV-2 infection rate. And to interpret the direct statement of the outcome, a greater infection rate is related to higher vaccination rates, and this conclusion is specific and only specific to the data collected for the month ending September 15th, 2021. And so we would further conclude that these results are statistically significant at the 5% type 1 error rate. So this ends our unit on correlation and regression and how it can be used to examine the effectiveness of various interventions on human disease.